I've got the power. Yeah, that sounds just like the actual song, right? Um, but we're going to talk about power today. Let's get into this discussion on what power is and how we can interpret it and how we can, yeah, those are the main things, how we can increase power. But this is the second video from 9.3b where we're going to discuss the power part. So this goal, interpret the power of a significance test and describe what factors affect the power of a test. So, quick definition for you. Power of a test against a specific alternative is the probability that the test will reject H naught at a chosen specific significance level when the specified alternative is true. In other words, let's put that into fewer words. The power of the test is the probability, too many B's, probability of rejecting H naught correctly, when you should. It's kind of the opposite of a type 2 error. Actually, it is the opposite of a type 2 error. All right, so that's why their actual values add up to 1. When we're interpreting a power, so this is kind of a way to do it. Let's say if the true mean or proportion is blank, meaning the alternative, so that's saying that's true, there is a blank % chance of finding convincing evidence for it. Okay? So if I want to look at an example, I can refer back to an example we've done before with this AAA battery. Finding p-values, we looked at like if this deluxe AAA battery would be worth their time. The power of the test to detect that mu is 31 hours is 0.762. Okay? Interpret this value. And it really should be greater than or equal to 31 because we're looking at the alternative hypothesis. So we would say if the true mean lifetime of the company's deluxe AAA batteries is 31 hours, there's a 0.762 or 76.2% chance that the probability that the company will find convincing evidence for mu being greater than 30. All right? That's how you can interpret it. Now I want to talk about some key parts with power. So the significance level of the test is the probability of reaching a wrong conclusion when the just ultimately the probability of rejecting the null, which includes a wrong conclusion when the null hypothesis is true. That is a type 1 error. Okay, talked about that last time. The power of a test to detect a specific alternative is the probability of reaching the correct conclusion when the alternative is true. So correctly. So type 1 error is incorrectly rejecting. Type 2 error is correctly rejecting. All right? We can just as easily describe the test by giving the probability of making a type 2 error, because type 2 error would be the opposite of power. So the power of a test against any alternative is 1 minus the probability of a type 2 error. 1 minus beta, we talked about beta briefly, would get you power. In other words, beta, which is the probability of type 2 error, plus power makes up every possibility, so it's equal to 1. All right? Now, typically you will not be asked to calculate power or the probability of a type 2 error. Those are just not things that the College Board expects you to be able to do. But you do need to understand what they are and the interactions among the errors, confidence level, the power, the effect, the sample size, how these things all impact power, and also how to interpret power. So I'm going to give a few points here, maybe some visuals, and then we're going to look at the key things that would help improve power, the correctly rejecting the null hypothesis. So power gives the probability of avoiding a type 2 error. Power has a different value for different possible correct values of the population parameter. Thus, it's actually a function where the independent variable ranges over the specific alternative hypotheses. It's going to get to a point that I'm going to make later. It's not a fixed value. It's something that can change depending on a lot of factors. So, number one thing I want to point out, choosing a small alpha value, that is making it tougher to reject the null. So like if you change from 0.1 to 0.05, that makes it harder to reject. So there's a smaller window to reject. It results in a higher risk of a type 2 error. Okay? And a lower power. So observed in the graphs below how making a smaller alpha makes the power less and the beta more. So I have an alpha level of 0.05, an alpha level of 0.02. That blue is all the reject range, but when you move it over farther, that creates a smaller reject range here, which means it's a lot harder, a lot easier to incorrectly reject as well. So that visual kind of maybe helps, maybe doesn't, but get the idea that if you make it tougher to reject, that makes it higher chance of failing to reject when maybe you should have. So it increases the type 2 error chance, lowers your power overall. The greater the difference between the null hypothesis parameter and the true parameter, okay, so you have your null hypothesis and your actual true parameter, the bigger the difference, the smaller the risk of a type 2 error, and the greater the power. I'll show you some examples in class, but if you move a solid graph higher, making the power greater and beta less, the difference between them is often called the effect, by the way. So the difference between the actual parameter and the null hypothesis is called the effect. Thus, the greater the effect, the greater the power. Another note, larger sample size. You increase the sample size, usually good things happen. It reduces the standard deviation, making the graphs narrower, and I do have pictures here. Maybe that can help. But that also increases the power. So if you change the standard deviation, it makes it a narrow graph, centers it more around the center, and it increases the power. Okay, usually larger sample size means good things. Now, I want to boil it down to a couple things here. How can we actually increase the power? So if those last couple slides were over your head, pictures didn't help, I get it. Power is a confusing thing. What can we do to increase the power? Because power is a good thing. It will decrease the chance of making a type 2 error. We can, like was just mentioned, increase the alpha level. Remember, a smaller alpha level makes it harder to reject, makes it easier to make an error. So increase the alpha level will decrease the level of confidence, but it makes it higher power. You can increase n, so that was that last one. It lowers variability in the sampling distribution, increases power. You can increase the distance between the alternative parameter, I think I spelled parameter wrong there, and the null parameter, which is make the effect. A little bit harder to do there, but the first two are probably best. And then, you know, by luck, you can increase the power. You can get a sample statistic that's extreme in the correct direction, and that will also help the power of the test. So ultimately, these things are not, it's a fluid thing. It's not a fixed thing. So a couple added notes here. Alpha and beta are inverse related, meaning, well, we don't need to know that too much, but they are inversely related. This is the one thing we talked about with how power and beta are related. Don't ever add alpha and beta together. It's not going to do any good. There's no formula that connects them. They are just inversely related. We just need to know that. So one example then, it says, the researchers in the Alzheimer's experiment want to test the drugs that manufacturers claim that fewer than 10% of patients who take the new drug for treating Alzheimer's will experience nausea, because there's always side effects of things. That is, they want to carry out a test saying that the true proportion, the null hypothesis would be that it's 10%, 0.1, And their alternative hypothesis is that it's less than that, because that's the claim. P is the true proportion of patients like the ones in the study who would experience nausea when taking this new drug. Earlier we mentioned that the power of the test to detect P, which I don't think I went through this one. Oh, I did talk about this. Or maybe I didn't. Is 0.08 using a random sample of 300 patients at a significance level of 0.05. The power is 0.29. Okay. Determine whether each of the following changes would increase, decrease the power, or maybe keep it the same. And explain. So let's say we used alpha as 0.01 instead of 0.05. So we're decreasing the alpha level. That decreases the power. Okay? Makes it more likely that there's going to be an type 2 error. Makes it harder to reject the null when the alternative is true. Okay? That will decreases. Second scenario, if the true proportion is 0.06 instead of 0.08, what if that was actually 0.06? That means it's farther away from the null hypothesis. That will increase power. If you have an increased distance there, it'll increase power. So that one will. Now if we use 200 for our sample size instead of 300, what would that do? Remember, bigger n is better. Bigger sample size. Smaller sample size decreases the power. Gives less information about the true proportion. Lower the n, lower the power. All right? So, to finish this up, power isn't fixed. I've said it multiple times now. It changes depending on what the alternative parameter is, and also all the other factors like the n value, the p value, or like the true proportion, the alpha level. These things all impact power. Power is a weird thing. I get it, but you need to understand the basics of it, how you can interpret it, and how you can affect power. That's the last part of section 9.3b here on power. See you next time.